Okay, so we're looking at the practice test B for 10.5, this section, and 10.6, 10.7, and 10.8. When we're looking at this, we're looking at the finding area of each polygon, and these are all triangles, except for the number 6. And then 7 and 8 are kind of interesting things as well, so we're going to talk about those. But basically what's going down for the triangles, the area is going to be equal to 1/2 BC sine of A. Okay, this is the side angle side area formula for a triangle. So I have 1/2 9 times 7 and sine of 73. That value, after I pop that in my calculator, is going to be 30.1 feet squared. So this is equal to 30.1 feet squared when I'm done with that. Okay, and we are going to group that information together. Bring that down and put it there so we can see it for the rest. But again, every one of these is area equal 1/2 BC sine of A. Area is equal to 1/2 BC sine of A. I'd strongly recommend to write these down. Folks are always wondering how I remember things, and it's because I keep writing them down and I visualize them. I reread them. And this is area is equal to 1/2 BC sine of A, where A is that angle made between B and C. Now, after I make my choice of formula with my shape and the information provided, it's just me plugging in. And interfacing with my calculator. And again, this is a triangle formula, side angle, side angle, side. So it's 1/2, 15 times 8, sine of 46. Okay, I plop that in my calculator, I get 43.2 centimeters squared. Here I've got 1/2, 8 times 10, sine of 30. I'm looking at 20 meters squared. Here, and 5, again, 1/2, 12, and 11, sine of 82. I'm plopping that in my calculator, 65.4 millimeters squared. Okay, my last one here, number 6 with my pictures, isn't a triangle. But remember, in a parallelogram, this is also 110 because opposite angles are congruent, opposite sides of the same measure, and this is also 18. So now I know that instead of doing the area is equal to 1/2 BC sine of A, that's one triangle. I multiply that by 2 for 2 triangles. So in this parallelogram, BC sine of A will work. So I've got 18 times 15 times the sine of 110. And I pop that in my calculator and I find out I have 253.7 yards. And that's squared. Okay, I'm going to take that, group it, and we're going to bring that down a little bit so it fits my area I have. Okay, so now a regular hexagon with an apothem of 3. Okay, if I have a regular hexagon with an apothem of 3, okay, so if I got a regular hexagon and it's got an apothem of 3, and this is a hexagon, Okay, let's assume it's regular. My apothem of 3. Well, if that's 3, and this means this is the square root of 3, and this is the square root of 3 because it's coming from that 30, 60, 90 triangle. Remember that this is 30, and it is. This is 60 and 90, and this is x, the square root of 3, and this is x. Well, if that's 3, x had to be the square root of 3. So we're looking at this, and I'm going to use 1/2 a and s. And 1/2, and a is 3. N's the number of sides, 6. S is 2 the square root of 3. Okay, and I'm looking, and I got 9, 18 the square root of 3 that I'm popping in my calculator, and I get 31.2 feet squared. A regular octagon with radius 5. Now the radius, this is awesome. Remember, I just did a problem with the apothem, but when you're given a radius, the formula we're going to use, area is equal to n, the number of sides, times the number of triangles, where r is the radius length, sine of a, which that's the central angle. So we're going to find the central angle, and maybe we'll have a picture of this so you guys can see what we're talking about. So we got an octagon. Got an octagon. Radiuses come from the center and go to vertices, and we're going to find the central angle. Remember, this is 5 and this is 5. So for finding the central angle, 360 divided by 8 is 45. Okay, so 360 divided by 8 is 45. Make that smaller. Those are there. Now I'm going to pop this in. I've got my side length. Green is a bad idea on green. I got my side length, which is 8, number of sides, I should say. 1/2. My radius is 5, and there's 2 of those, so we're going to square it. And I got the sine of 45. I'm looking this over. It's sine of 45. And now I've got 25. Half of 8's 4, so I got 100. Sine of 45 to put in my calculator. And I'm looking at this being 70.7 feet squared when I'm done with my area. Okay, now that's the end of 10.5, and those are the formulas that we've been using. In 10.6 review, okay, the formula that we're going to be looking at, we got 2 parts here. We're asked to find the circumference of each circle and then find the length of the arc shown in gray. So the A part is circumference, and circumference is 2 pi r. Okay, and this one, and I'm supposed to leave in terms of pi. I've got my radius is 3, but I also look at diameter times pi for circumference, and I've got 6 pi. That's my A. And I'm going to do the A all the way across. So, and the A for 10, I've got, again, circumference, and I'm just going to go diameter times pi because they give me diameter. It's 20, so it's 20 pi. And I've got circumference here in my 11. Okay, I've got my circumference is equal to 2 pi r. R is 9, so 2 times 9 is pi, it's 18 pi. Okay, and each of these, by the way, should have centimeters, and this is feet, and this is centimeters, and they are to a single power because it is just length. So in looking at this in 12, I've got the same idea with circumference. For the A part, I got circumference is 2 pi r, and pi is, my radius is 5, so I got 10 pi. And my A in 13, I've got 2 pi r again for circumference. My radius is 7.5. My diameter is 15, so I'm going to grab the diameter. It's 15 pi. And this is meters. And back here it's inches. And we're looking back here in 14, A, circumference is again 2 pi r. and I've got 4 for my radius. So 2 pi times 4, so I get 8 pi feet. Now, those are all the A problems, okay? Now, the B problems are our next issue. So we're going to look this over on each one. Okay, so now we got the A's done, and now let's look at the B's. In the B problem, they're asking me to find this length. Now that's a percent of what we already found. So keep in mind how we do that when I'm finding that length. We will use arc length. So I'm going to go the length of my AB is equal to measure of arc AB over 360 2 pi r. Now, my arc length is 240 degrees here because this is already 120, but the solid is 240. And since the solid is 240, we're finding the length of the arc shown in gray. Oop, I lied. We're finding the arc shown in gray, but we want the bold arc. We're doing the bold arc on each one of these. It says in gray, but we're doing the bold arc. So the bold arc is what we're going to be finding. So we have this is 240 over 360, 2 pi times r, which is 3. Okay, so if we take that 240 divided by 360 times 6, we get 4. So this is actually going to be 4 pi centimeters when I'm done. Okay, so I got 4 pi centimeters when I'm done after I pop everything in and get this going. Now on the test itself, if you have a question on which you're supposed to find, which arc, I won't tell you about any values you're supposed to use. That's your job to ask and make sure you clarify that question. Okay, now in 10, same idea. I'm looking at this. This is 150. This is 180. So I've got a 180 plus 150, and I've got a 330, so this is 60. Excuse me, this is 30. This is 30, and I'm finding a 360 arc. So we're going to take care of this and get this out. So again, my B value, I'm going the length of arc AB is equal to the measure of arc AB over 360, and that's going to be with my 2 pi r. In this case, we already found my circumference. So I'm going to be looking at 330 over 360, and we got 20 pi we're going to be working with. That's my circumference. And so I've got 330, 20 pi, 330 divided by 360 times 20, and I got 18.33, but I use my fraction on my calculator, and I get 55 thirds, 55 pi over 3 is my final answer. Okay, and that is feet. Now my next one that we're working with, well, let's do this way. We're going to group this. We can work with that in a little bit. My next one's still the same stuff. I've got 90 there, and the remainder of this is 270. So 360 minus 90 is 270. So my arc I'm going to be working with is 270 degrees. So my length of arc AB is equal to my measure of AB over 360, 2 pi r. And we already found 2 pi r, that's 18 pi. So now I'm going 270 of 360 times 18 pi. So I got 270 divided by 360, 270 divided by 360 times 18. And that's 13.5, and I'm going to go to my frac, and it's going to be 27 pi over 2. And that is in centimeters. So again, I'm just going to group these. Get this smaller. Move things along. Extend that up. So this last one, this is 225, but I got 360 minus 225. So I got a 135 degree arc I want to look for. Okay, so now in the B, I'm looking at my arc length. My arc length is of AB is 135 divided by 360 times my circumference, which is 10 pi. Okay, and remember the formula we're using of AB is the measure of AB over 360 2 pi r. So with that stuff plugged in, 135 divided by 360 times 10, and it's 375. So I got 375 pi, but then I got to put it in my fraction, and it's 15 pi over 4. Okay, now this one I got 45 and 180. So 45 plus 180 is going to be 225. So this is 225, and I've got my length of arc AB is equal to the measure of arc AB over 360 2 pi r. I already found 2 pi r, that's 15 pi. Okay, so the measure is 225 over 360, I got 15 pi. So I got 225 divided 360 times 15, and that's going to be 9.37 pi, 75 pi. But I got to put it in fractions. So I got 75 pi over 8. Notice I'm not rounding those to the 10th or 100th because they terminate. So I have all my value there, and I've got, this is in meters. Oh, and the one previously was in inches. Okay, in 14, when I'm looking at this, same formula. The length of arc AB is equal to the measure of arc AB over 360 2 pi r. And I've got this set up as 144, so I got 144 degrees over 360 times 8 pi. And that's what my 2 pi r is, 8 pi. So I got 144 divided by 360 times 8. And that's 3.2 pi, but it's as a fraction. I've got 16 pi over 5. Okay, and that is in feet. Now, as we slide on here, and we save things, let's bring this down a little bit so I can actually function a little bit. A bicycle wheel has a radius of 0.33 meters. Okay. And I've got how many revolutions does a wheel make when the bicycle is ridden 1 kilometer? Round to the nearest whole number. Well, how many revolutions does a wheel make? I've got to look at this and go, well, circumference is equal to 2 pi r. That's going to give me the distance of 1 revolution. So since the radius is there, I've got 0.66 pi is 1 revolution. And this is meters. Okay, so that's 1 revolution. So they're asking me, how many revolutions does a wheel make when the bicycle is ridden 1 kilometer? Okay, so if I've got 1 kilometer, I got 1 kilometer. Okay, and a kilometer has to be switched over from kilometers to meters. How many revolutions? Well, I've got to go revolutions, so we're good. But we got meters here. So I'm going to make kilometers meters. So I know that there's 1,000 meters in 1 kilometer. So that's now meters. But now I've got to go from meters to revolutions, and I know 1 revolution is 0.66 pi meters. So now I'm going to have my answer in revolutions, and I multiply those things with my calculator. I get 482.28, and so I'm supposed to round, so there are 482 revolutions in 1 kilometer. Now, this next set is sector area, okay, from 10.7. So I'm working with sector area in 10.7. And in sector area, I've got sector area. And that is, gosh, it's the arc measure of AB over 360 pi r squared. Please notice this is area of a circle, pi r squared, and what we were doing before is circumference of a circle, 2 pi r, okay? But now I've got my stuff going on. I got 360 minus 240, that's gonna be 120, so I've got 120 over 360 pi r squared, and I'm supposed to round the nearest tenth, so I'm pi 7 squared here, and I've got my answer is 51.3 feet squared. Now, keep in mind, this is the formula I'm going to use each time, and we're going to clone it and move it along, and we're going to clone it and move it along, and we're going to make it a little smaller. We can make adjustments. Matter of fact, I'm going to make these smaller, otherwise I'm going to have a problem with this other stuff. Okay, and we're going to clone it. Bring it down here, we're going to clone it. Well, I can't clone that, can I? Those are different values. So we're going to do this with that one, we're going to do that with that one, and then we're going to do a different formula entirely for these. So I'm going to cut that. So here's the deal. These 3 that I have set up in green are all the same. Sector area, I've got, this is 135, 180 minus 135. Is going to give me a 45. So I got 45 out of 360 pi 9 squared. Okay, there. And that's 31.8 centimeters squared. Here, I've got 200, so I got 160 over 360 pi, again, 9 squared. And that'll be 113.1 yards squared. Okay, but now, keep in mind, those are just straight up formulas. And now I have some really funky things going on. I've got those segments of circles that we did yesterday. And you got to make sure that you're comfortable with them segments of circles. And we're going to use those as blue. The segments of circle, I'm going to use my sector area formula because I got to find the sector area, and then I got to subtract off a triangle. So I'm going to subtract off a triangle. So I'm going to use the triangle formula with angles, and this is what we'll do. So I got the sector area, and I've got my triangle. So this is going to be 60, 180, so it's 120, 360, pi 6 squared minus 1/2. Remember, radius is 6 squared sine of 120. And this is going to be my sector area minus my triangle. And that's what we've got going on here. We got the sector area we find first. Okay, that's there. And then we're going to subtract off this triangle. That's there. Okay, so keep that in mind when we're going through this problem. Now, after I do this, I pop it in my calculator, and my final answer is going to be 22.1 inches squared. Okay, if you got questions on popping in your triangle, make sure you ask about them after school today or during work time today. That's what we're doing. All right, so we're going to do another one. I would do one by myself if I were you, make sure I was comfortable with it before I check the solution. Now that you have the formula to work with. So this is 90, so it's going to be 90 out of 360. That's 1/4 pi 4 squared minus 1/2 4 squared sine of 90. And our final answer comes out to be 4.6 meters squared. Okay, so that's equal to that. That's 4.6 meters squared for our solution there after I plop that in my calculator. Remember, this is all about formula identification and knowing where everything is to put in your calculator and get things done. I'm going to do the same thing with the formula here. I've got 360 pi r squared because it's area minus 1/2 r sine of my angle, and this is 120. So I've got 120, 360 pi 4 squared minus 1/2 4 squared sine of 120. And I've got my final answer to be 9.8 millimeters squared. Okay, now in 22, a 14-inch diameter pizza is cut into 6 equal slices. About how many square inches of pizza are in each slice? Now they're asking for each slice. I got a 14-inch diameter pizza is cut into 6 equal slices. So we're doing that sort of thing. Let's assume all those slices are the same. Okay. How many square inches of pizza are in each slice? So I know right now my radius is 6, and now I've got 360 divided by my radius is 7, so I know I'm not going to do anything fancy. I just know that I'm going to equally split up my area. So I've got area is equal to pi r squared, and I'm going to take and split my area of one slice 6 even ways. So we're going to find my area first. Pi r squared, so I got pi 7 squared, so I got 49 pi. Now, one slice is 49 pi over 6, and that is the same as 25.65 inches squared per slice. So they say round to the nearest square inch, so this is about 26 square inches per slice. Now, in this next one, darts are thrown at random at each of the boards and shown. If the dart hits the board, find the probability that it will land in the shaded region. Well, you gotta kind of figure out what's going on with our shaded regions. If I split this one up, and this one's kind of nice to do this way because it's a square, and I have, what I just did is created 2 more slants in there with the other diagonal. So I have a total of 8 sections, 8 segments. So 2 out of 8 are shaded here. So 1/4 is my probability. If a dart hits the board, find the probability it will land shaded. So my probability land shaded is going to be 1 out of 4, or 25%. Now in this next one, in 24, I have my triangle evenly split up from the center to the vertices. So these are all 120, okay? They're 3 equal parts. So again, probability land shaded here is going to be 1 out of 3, okay, or 33 1/3%. Now, going on with this next one in 25, I'm supposed to figure out the probability I'm going to land shaded. So on this, it really comes down to I've got 105 degrees, and I should probably write out my probability. I've got 105 degrees I'm really interested in, and the probability land shaded is equal to 105 over 360. I mean, as straight up as I can get it, I'm not going to do anything else. I could do the total area, but since it's consistent going through, I'm just going to go through the parts that I have in these areas, okay? Now, in this rectangle, these are all split up evenly as we go through. So I have, once again, 1, 2, 3, 4, 5, 6, 7, 8 triangles that are identical. So I got a 3 out of 8. Probability shaded is 3 out of 8, okay? Now, in 27, I'm going to have a harder time. I've got to be talking about my dartboard a little bit differently. I've got probability in the land shaded. To find the top over the total, I've got to figure out what's going on. So I'm going to go big minus little over big, okay? So now the big has a radius of 6, so I've got 6 squared pi, 6 squared pi. The little has a 4 squared pi, okay? Now, I got 24 minus 8 up there, divided by, 36 minus 16, okay, on the top, and 36 on the bottom. So now my probability shaded is going to be 55.6% on that one. Okay, arcs in this next one. I've got arc BF, minor arc. Minor arcs are named with 2 letters. Major arcs are named by 3 letters. So I go over here. Remember, I start at one, I end at the last one, and I go by way of the middle when I'm thinking about these major arcs. That's a D. Okay, and this last one I got BFE for my semicircles, ECB, CBF, and FEC. Semicircles start and end at a endpoint of the diameter. Major arcs are more than the diameter. They're more than 180 degrees. Minor arcs are less than 180 degrees. Now, on this next one, 32 is 128. Okay, that's TC, and I go TC, that's straight up. And if that's 128, then I've got this is 52. This is also 90. Okay, when we're looking through, now I just add things up. TBD is 180. BTC is 90 plus 28, which is 218, and these are all degrees. TCB, if I go TCB, is 180 plus 90, which is 270. CD is just 52. CBD, remember CBD goes around this way, so it's 360 minus 52, which is 308. And 38, I got CPD, and CPD is this angle. Okay, and then notice the change, notation, and that's 52 degrees. And then angle CPB is 52 plus 90, which is 142. Now these last two is all about segments, okay? So I'm looking at what's the probability that my point, chosen at random, point is on CD. Remember, CD, okay, so I've got to go CD over AK, right? And CD is just 1 unit. AK happens to be 10, so I got 0.1 or 10%. And GK, probability, my random point is on GK, okay, is equal to GK over AK. And that is going to be, if I've got GK, K is 10, G is 6, 10 minus 6 is 4. And then I'm looking at the whole length, which is 10, so I got 0.4 or 40%. Okay, I hope those things helped. If you got questions, please let me know. That's what we're going to be doing today, and we'll see what we can get done on other things. Have yourself a great day.